So why do we have logarithms and where do they come from? So the original use of logarithms was actually to be able to convert long multiplication problems into simple addition problems. And so what people had is they had these log tables, and they could turn long multiplication problems. For example, if you wanted to multiply 3,396 times 4,656, you can imagine that it would take a long time to be able to write out that calculation by hand. But with log tables, they could simply look it up, and because logarithms essentially turn multiplication into addition and division into subtraction via our exponents, they can easily, it's much easier to be able to add something than it is to be able to long multiply these numbers out. And you can look up which exponents to be able to add. And so logarithms were actually invented in the 1600s by the Scottish mathematician John Napier. And he did it between 1594 and 1614. And the reason he did this is, again, to be able to simplify these calculations. And so eventually Henry Briggs, he compiled the first log table so that we could be able to simplify these tough calculations without a calculator. And so you have to know that this is a time that's before calculus, before Newswork, before Leibniz, before Gauss. And so we didn't have calculators, of course, and we needed a way to be able to turn these multiplication problems into addition in the 1600s. So how do we turn multiplication into addition? How do we turn division into subtraction? How did they used to use log tables? So let's say we want to multiply 37 times 59. So what we can do is we can express both of these as base 10. And so 10 to something is equal to 37 times 10 to something is equal to 59. And so how do we get these numbers? Well, we would look them up on the log table. So we see that log of 3.7 is 0.5682. So this means that 10 to the 0.5682 is equal to 3.7. I know it says 37 here and it says 562, but there should be a decimal point here. This means 3.7 and this is 0.5682. So 10 to the 0.5682 is 3.7, which means 10 to the 1.5682 is 37, which I'll show. And similarly, we can 59, so we know that 10 to the 0.7709 is 5.9, so 10 to the 1.7709 is 59. So this is that. And not just looking up at log tables, but we can just kind of understand why this equals to 37. If we look at, if you know that 10 to the 0 is equal to 1, and you know that 10 to the 1 is equal to 10. And so, you know, if you want to obtain 3.7, you want to obtain 3.7, that number is somewhere in between 0 and 1. And so it's closer, because log is a function, exponent, it's like an inverse of an exponential function. It's closer to 1, that number, so this 3.7 is closer to 1 than it is to 10. But that's 10, how many magnitudes of 10 do I have to raise? What power do I have to raise 10 to be able to get to 37? So how many magnitudes of 10 are in 3.7? And the answer to that is 0.5682. So about halfway through, if between 0 and 1, about 0.5682, we get 3.7. And so that's how you kind of understand where you get this value from, but also what we would do is actually just look it up on the log tables, which is quicker. So that was just kind of understand what's going on. But if you look it up on the log tables, you can see that this is log of 37 is equal to 1.5682. So anyway, what we would do is we would add these exponents. So this is equal to 10 to the 3.3391. And so once we add those exponents, because they're both base 10, and then you could look that up on the log table and see what the value is and get your final answer is 2,153. You can imagine that it's much quicker than being able to multiply these out and do them by hand. But if all you need is to be able to express 37 and 59 as a log base 10, see what magnitude of 10 or what power of 10, how many magnitudes of 10 go into 3.7 or 37. And so how many magnitudes of 10 go into 37? It's 1.5682. How many magnitudes of 10 go into 3.7? 0.5682. And so we would just look this up in the log table, see how I get 37, and see here to get 37 we get 10 to the 1.5682 is 37. And then we would look it up for 59. 10 to the 1.7709 is 59. And so once we are able to express both of them as base 10, which we can easily do by looking at the log tables, we have just turned this multiplication problem into addition. And so looking it up on the log tables via our exponent rules, we can do this really quickly because we can just add these exponents because they're both base 10. As long as these bases are the same, we can add these exponents. And so we just turned this multiplication problem, this 37 times 59, we just turned this into addition by turning them into exponents and expressing them as both base 10. So by raising both of these by expressing both of these numbers to the same base, we're able to turn this multiplication problem into addition and do it really quickly. And you can imagine that's much quicker than being able to multiply by hand. And so we get by expressing in a base of 10, we're able to turn a multiplication problem that traditionally we would have to multiply by hand like this, which you would still get the same answer, of course, but that's much more time taking and then being able to just look it up in the log table and do it really quickly. And so this is a really quick way to be able to do these multiplications just using the addition and using our exponents and using these log tables. And so how do we use these log tables? So this, it says 37 and 5682, but it's actually 3.7 and 0.5682. So this is really saying that log of 10 of 3.7 is equal to 0.5682. That's not what we need. We need log base of 37. So how do we get that? We just multiply, both sides, we multiply 3.7 by 10, and we need to add this magnitude of 10 to this. So this would just be 1.5682. And just so that you see what I mean, we can express this as 10 to 0.5682 is equal to 3.7. Again, we're just adding one more magnitude of 10 to this, so that's why we add that 1 on there. And so we multiply both sides by 10, and so you would get 10 to the 1.5682 is equal to 37. And so you can see just to be able to get log of 37, we'll just add one more magnitude of 10, one more exponent. So that's why we get that 1 over there. And so if we wanted to do 2 magnitudes of 10, so let's say this was 370 and not 37, then we would add 2. So that would be 2.5682 because that's 10 to the 2 plus 0.5682. So that's 100 plus that value. So you can see this would be log of base 10 of 37 is equal to 1.5682, and we would use that right up here, and we can see indeed 10 to the 1.5682 is equal to 37, and so we can use that to be able to express it. And so that's how we obtain this from the log table. Similarly, just to show you, if you wanted to do log base 10 of 370, you would just multiply this by another, instead of magnitude 10, you would multiply this by 2, 8, and you would multiply this by 2, and that would be 10 to the 2, 10 to the 2.5682 equal to 370, just so you see how it works. Anyway, we get this log of base 10 of 37 is equal to 1.5682. Similarly, we see this log of 5.9 is equal to 0.7709. So to get log of 59, we add that 1 base 10 up there. So log of 59 is 1.7709. And so indeed, you can see that right here. And so we can express these as a magnitude of 10, 37, and 59. And then we add those exponents and we get 10 to the 3.3391. And then we would quickly look up, be able to look up 3.3391. And this is just a zoomed in version of this. And we can see that answer is 2,183. And this column is just for adding additional digits on there. And you don't really need to worry about that. But that's basically how you used to use logarithms and tables to be able to simplify these addition problems into these multiplication problems into addition. And similarly, if you wanted to do subtraction, it would be the same thing. Rather than, or you want to do division, it would be the same thing. You would rather do subtraction. So, for example, you would still be able to use these log tables in a similar way. But let's say we just had 37 divided by 59. You would just do, you would just express these in base 10 again. So you just do 10 to the 1.5682 over 10 to the same thing, but just look it up. So then we got 1.7709 for 59. Then that's just you subtract these exponents, and you would just do 10 to the 1.5682 minus 1.7709. And you would look that up on the tables and obtain the answer. But that's just how they used to be able to simplify multiplication into addition, division into subtraction, and be able to convert these operations and do it in a simple way using the log tables. The issue was that these log tables weren't as reliable. They had up to 4 sig figs, and they could have more, with more accuracy and more digits as people develop more tables, but they weren't that reliable. And nowadays, our calculators can do any number of sig figs. They can do it to a very, very high accuracy really, really quickly because of the computational power and microprocessors and everything that we have today with calculators. But this is how they were able to do multiplication problems and long number multiplication problems and log addition problems by using these log tables and being able to do them quicker than being able to write it out by hand. But the use of logarithms doesn't stop at just being able to do multiplication into addition, or subtraction. It's actually very useful to visualize logarithms as this magnitude and this scale and be able to use it in the form of using scales. And I'll show those examples later. But just to show how did they generate these log tables in the first place, and how did people write these out? And so I'll show an example here just to illustrate that really fast. And so you can see if let's say a is equal to 1 minus 0.1. So notice we're expressing it in magnitudes of 10, and raise that to the 10th power. So how do we calculate that? Okay, let's raise this to another power. Let's raise this log base down, so 1/10 of it. Let's raise it to 0.1. Would that make it easier? Yeah, because remember the exponent rules, we can just multiply if we have 2 exponents on the outside. So what would this be? We could just pull this here. And this would be the same thing as raising this to the 0.1. And so we could just multiply these out, and that would just be equal to 1. So that would be equal to 49. And so we can just simplify it that way. And so similarly, if we keep on going, we go a to the 0.2. And then we, again, have this original one. And we raise that to 0.02. And we multiply this out. That's the same thing as raising this to the 2nd power. this to the second power, right? 10 times 220, 20 divided 2 is 2, and 20 divided 10 is 2. And so we go to raise this to the second power. And so this, we can express this. You probably know this is 0.9 times 0.9, now that's 0.81, but we can just write it out just to show how we would be able to simplify these calculations. So we can do 0.9 times 1 minus 0.4. Right, the same thing, that's just multiplied again. And so you can distribute that, and that's equal to 0.9 minus 0.09, and that's equal to 0.81. So this is how they would simplify these. They would just keep on going, and they would get, they'd be able to generate these log tables by generating these different base 10s and generating the values for them. And they would put these all in the table so that people could search them up. So let's say, for example, we had a 0.3, and that would just be equal to 0.81 minus 0.081, and we did 0.729. And so now we have something like 0.3. We have a value for that, 0.729. And that's how they generated these log tables. And so they could convert between base E and base 10, and for greater accuracy, they would use this kind of thing, and this was called not here space. And so that A value that we set above is not here space, and they would use this for greater accuracy. And so that's basically 1 minus 1 to the 10 to the 7th to the 10 to the 7th. And so this was how they would generate these log tables. They would keep on going and write these calculations out and generate the exponent's power so that people could be able to easily use the tables and do these multiplications. And so I just did this. It's not as important to see this because obviously right now we have calculators, but this kind of demonstrates their thought process into how we used to be able to look at these magnitudes of 10 and be able to use that base system to be able to do these calculations and what logarithms really are. And so nowadays, yeah, of course, logarithms, we don't use logarithms to be able to do multiplications and turn multiplications into additions and use our log tables that way. But it's useful. We do still use logarithms nowadays as an example for being able to understand how magnitudes of numbers. So I hope that was kind of helpful to kind of see how these log tables were used and how they work.